So in 1905, Albert Einstein proposed a theory that explained the results of Michelson-Morley experiment and completely altered our notions of space and time. And he based this theory on two postulates. One, that all the laws of physics are the same in all inertial frames, and that includes the laws of electromagnetism, and the constancy of the speed of light, which is this speed here, about 3 times 10 to the 8th meters per second in all reference frames, regardless of the velocity of the observer or the velocity of the source emitting the light. Now, the consequences of special relativity, and I think they get this in the right order, they say on the very first thing they start talking about is the concept of simultaneity and why Einstein had to abandon it. And what I'm going to do right now is show you a couple of demonstrations that try to show why you have to abandon the idea of simultaneity. And the first one, I think, I'm going to go straight to this one first. The circular mirror shows how a Lorentz contracted circular mirror interacts with flashing and returning light. When viewed from a reference frame where the emitter and circular mirror is moving, the events where the flash of light meets the mirror are not simultaneous. So let's go ahead and look at that. Okay, and here's the animation here. The circular mirror doesn't look circular, first of all. It looks like an oval. And what we have is a circular wavefront going outward at the speed of light, bouncing off the mirror, and then moving back inward. Now, if you were actually standing in a position, or if you were actually moving along with the mirror, instead of seeing these events as being, where the light flash meets the edge of the mirror would be simultaneous. But in this reference frame, they are occurring from the back towards the front and then coming back to the center again. I can actually adjust some of this by changing this value here. This value is called the rapidity, and I can change that rapidity so that instead of having a rapidity of 0.5, which I had before, now it is rapidity 0. With the 0 rapidity, this is what the view looks like from the point of view of someone traveling at the same speed as the mirror. The flash goes out, hits every side of the mirror simultaneously, and comes back in. I can make this number much larger. Now this is not, p is not the speed of light, but is the hyperbolic arctangent of the speed of light, or hyperbolic arctangent of the velocity of the mirror. So you can see, depending on how large this gets, you get a very, the animation isn't quite perfect. It seems to flub up a little bit there. I may not have correctly assigned the relationship between velocity and rapidity. Actually, I think I did. I did it right. I was looking at something that I expected to be aligned, and it's not aligned. The blue line here follows the intersection of the purple wavefront and the red line. So you can see that the red line there that goes through the middle is where the purple line and the blue line meet. Okay, another animation that I want to look at is the flat moving photon clock. And this one actually has 3 different settings for the 3 photons of light passing back and forth between 2 mirrors. The Lorentz transformation changes the synchronization of the photon collisions and orients the groups so that the direction of travel is perpendicular to their direction of motion. So again, I will click on that and see what that looks like. Okay, right now the rapidity is at 0.9, and if I slip that down to to 0, you can see the photons just bounce straight back and forth, and they're all aligned. But as I move the rapidity forward, the 3 photons kind of hit the mirrors at different times, and so that but they still travel in a direction that is perpendicular to the wave front. You can see the difference between Lorentz transformation and Galilean transformation by moving the selection from 1 to 2. And you see in the Galilean transformations of these events, the photons don't orient themselves so that they're traveling perpendicular to the wavefront. But with the Lorentz transformations, the time is desynchronized so that they do. Okay, now let's talk about time dilation for a second. That is the next thing that comes up on the text, and it's actually the first numbered equation in this chapter. Related to time is distance traveled divided by speed. So here you can imagine that these photons are moving from here to here to here. They're traveling at the speed of light. So, oh no, I'm in the wrong context here. Okay, they're talking about the proper time here, which is going to be 2d over c. And I don't want to call the distance from here to here d. Rather, let's move this down to 0. I want to call the distance from here to here d. So this is the proper time. The proper time is as the photons move from here to here and back to here. So that is going to be 2d over c. But now we're going to look at this from another point of view where the photons are traveling, something like that. Now, the base of this triangle has a length of the velocity of the clock times the time, while the hypotenuse of this triangle has a distance of the speed of light times the time. Okay, but we've already used the time being there and back again, so we're going to call this c delta t. Sorry, I'm not pointing in the right place. The hypotenuse here is the speed of light times half the time. The base of the triangle is the velocity of the, well, in this case it's a picture of a train, the velocity of the train times half the period of time. And this distance here, the opposite side, is the distance, the height of the train. So this is a right triangle, so we can just apply Pythagorean theorem to it. The base squared plus the opposite side squared is equal to the hypotenuse squared. Okay, to simplify this problem from the text, I'm only going to consider the time as the light beam goes from the bottom to the top of the railcar, instead of going from bottom to top and then bottom again. In other words, I'm just going to look at this part of the triangle, and I'm going to call that v delta t rather than v delta t over 2. I'm going to look at this part of the triangle, call that c delta t instead of c delta t over 2. And I'm going to call this, I'm still going to call this d. So d, I'm also going to not put a 2 in over here. So d over c is going to be equal to the proper time, but I'm not going to call it t sub p. I'm just going to call it tau. So right here, where they have a d squared, step b right here, I'm just taking that d squared and replacing it with c delta tau squared. So that is pretty much where we are. So while the description in the text solves for delta t, then later replaces d with 2c delta t sub b, I've elected to make the replacement d equals c delta tau immediately. And this delta tau is the time a hypothetical observer aboard the train would experience as the flash of light is on its way between the floor and ceiling of the train. Okay, steps C, D, and E are all just algebraic, and we're trying to get the delta t over delta tau here. And step F is something a little bit extra. F goes one step beyond the text, making note of the hyperbolic nature of the result. So delta t over delta tau is the hyperbolic cosine of the arctangent of v over c. Basically, the arctangent of a velocity will give you something called the rapidity. And then you can take the cosh of the rapidity and you get the time dilation factor. So let's see that. Y equals 1 over square root of 1 minus x squared. That is right there. Y equals cosh of arctangent x. That is right there. And you can see that in blue. You can see that you can see that in red. And they are exactly the same graph. Another thing I can do with this is say y equals x over square root of 1 minus x squared, and I can say, make this a sinh, S-I-N-H, and you will see that also is exactly the same graph. And finally, y equals x, and y equals tanh of arctangent. You find those are pretty much the same graph except for one minor detail. The hyperbolic tanh has a domain of -1 to 1, while y equals x goes all the way from negative infinity to infinity. That is because if I put in something like an arctangent of 5, I get undefined, but 0.5 works out fine. But the point of all this is that the person that observes this, the person that observes the photons going straight up and straight back down again, sees actually less time pass than the person that sees this, that sees the photons moving at the speed of light towards the mirrors as they are moving along. I can bring that down a little bit. So it is possible for quite a bit of time to pass if those mirrors are moving very, very quickly. I think I'm going to go ahead and go outside the text completely for a second to talk about how you would use the Lorentz transformations to kind of think about this problem. When you're on board that train and you think about the two signals, one of them happens down here and one of them happens up here. Let's actually do and so what is the delta x between those two times? The delta x here is going to be 0 because the train is not moving in that direction. And the delta t is going to be d. Yeah, c delta t is d. So this is going to be what we're going to plug into the equations. Now the way matrix multiplication works is I multiply 0 times cosh phi minus sinh phi times d. So we're going to have a minus sinh phi times d. And then and that's going to be delta x prime. And then for delta ct prime, we're going to have 0 times negative sinh phi plus d times cosh phi. And then, okay, that d was c delta t, so let's just focus in on this part of the problem. Delta ct prime equals ct delta ct cosh phi. Now, I think I may have reversed the proper time. This was the this was the proper time between the events, and now this is the observed time. So I did kind of screw up the notation a little bit from the start there, but otherwise you can see that we do get that delta t over delta tau equals cosh phi in this situation. All right, I wanted to take a brief detour and talk about gamma ray telescopes. They don't function the way you might think they do. These gamma ray telescopes, here one's described. The body of the Hess camera houses 60 drawers, each containing 16 photomultiplier tubes and the associated electronics, and power supplies, trigger logic, processor for data readout. The camera has a diameter of 1.6 meters and an active field of view of 5 degrees. So how does this thing work? Well, it works by detecting something called a cosmic ray. And here's a typical cosmic ray occurrence. Here's your gamma ray photon coming in. You get these pi mesons, the muons here marked with the letter mu, then more gamma rays, and then those gamma rays hit molecules and stuff like that and break them up into electrons and even, what is this? E minus and E plus? Goodness, those are positrons. In any case, those are generally generated in the upper atmosphere, and if they are detecting them in one place, they're probably detecting them in another place, so they can triangulate and figure out exactly where those muons are coming from. That's the purpose of those gamma ray telescopes. And when the muon is created, it has a half-life that is long enough that it should travel about 650 meters. If it were traveling at non-relativistic speeds. However, because it is traveling at relativistic speeds, it has a much longer half-life, and many of them actually reach the ground, a much larger number than would be predicted by their half-life and the number that are being generated. So this is one of the commonly cited pieces of evidence that the time dilation actually happens, is that there are so many more muons detected by gamma ray telescopes than would have been predicted by Newtonian physics. So you can think about it this way: if you move really, really, really fast, you don't have as many heartbeats, but you also live longer. So you will be wanting to be careful when you're talking about periods versus frequencies, because when you have when you watch something moving very, very fast, it has a slower frequency and a longer period. So the frequency goes down and the period goes up.